In section 29, we're looking to model exponential functions. So to do this in activity 1, we started off with an activity on paper folding. So the basic idea is that if you take a piece of paper and you don't fold it at all, you will have one section, the entire piece of paper. And the fractional area is 1. It's the entire sheet of paper. If you fold the paper once, and it doesn't matter how you fold it, but you'll end up with 2 sections. And each section will have a fractional area of 1/2 of the entire thing. If you make 2 folds, you will now have 4 sections. And from there, you'll have 1/4 the area for each of those sections. And that pattern continues. So essentially what's happening here is when you fold, you're doubling the number of sections that you started with. And this would be an example of an exponential growth relationship. So you have an output and you're doubling it every single time. You're multiplying by 2. The fractional area, however, is an exponential decay relationship because we're taking 1 and we're multiplying it by 1/2, multiplying that by 1/2 to get 1/4, and so on. So our pattern there, our decay factor would be 1/2. So on the back of that page, we had the exponential growth model, and we graphed f of x. So we had our points. So again, x was the folds, and sections was f of x. And we graph those to get this relationship here. Again, we've got these points, and you can see very quickly this graph will jump up very fast. And we don't even have all the data here, because if we went to 7, we should be at 128, and that's way off the chart. And even at 8, that's even worse. So is the graph linear? No way. It's not a straight line, and there's this dramatic increase that starts to take place around here where greatly changes the slope. And how can we have determined that from the table before graphing it? Because we know we've multiplied each value by 2. So then how do we actually write the equation? Well, we have to start off with an initial value. And our initial value was 0 folds. So in 0 folds, we had just the one section. And each time we folded, we doubled the number of sections that we had. That's what's called our growth factor. So when we're creating this growth model, we're going to take our initial value, which is A, it's 1 in this case, and our growth factor, which is 2, and that's B, and just plug those in. So our function then is 1 times 2 to the x. And now we can simplify that further if we want to, because 1 times anything is just what it is. For the exponential decay, we took our x value, which was the number of folds, and g of x, which is the area that each one of those folds takes, or each one of those sections takes up. So again, our initial value was 0 and 1, so we plotted that point and plotted all of the a good portion of the other points. And we can see that we have an exponential decay graph. Very steep slope, and then it kind of levels off towards the end. So is the graph linear? No, it's not a straight line. We've got that dramatic decrease in the beginning, and then it kind of levels off. So will the answer for g of x ever reach 0? And it seems like it is. It's really getting really close to 0, but it's never actually going to get there. So it won't, because half of any non-zero number will always be a number. It's never going to be 0. And just like we did with the growth model, the decay model is set up in very much the same way, except now we have this number 1/2. That's our decay factor. If this number is between 0 and 1, it's a decay function. So a b between 0 and 1 is decay. If b is greater than 1, then we have a growth function. So again, we take our initial value, 1, our b value, 1/2, just plug them in to get our function. In activity 3, we're taking context situations and determining if something is linear, exponential growth, or exponential decay, and then trying to figure out a pattern to that. So on this activity here, we had the green ones are the ones that are linear. So situation B, a town's population growing by 1,700 people each year, would be a linear situation because we're adding the same exact amount every single year, $1,700 or 1,700 people. In E, Marissa invests $300 at a bank that offers $5 of interest every year. We're adding $5 every single year. It's not changing. In H, Terry's at the top of a ski hill at an elevation of 3,000 feet. He's losing 70 feet every second. So we're subtracting 70 every single time. It's not changing as far as what we're decreasing by. And then J, Matt bought a used car at a cost of $35,000. The car depreciates at $5,000 in value each year. We're losing $5,000 every single year. So then we get into the ones that are exponential. So those are the ones that are in the green and the purple. And a dead giveaway for the most part is going to be the percent. If you're increasing by a percent or growing by a percent or maybe decreasing by a percent, it's usually an indication that it is an exponential function. Another is words like double, triple, half. Those are indications that we're multiplying by something to get our subsequent values. So in part A, part C, and part I, we had an exponential decay. The value is decreasing. Sometimes the words are obvious. Decreases. So it's going down. We know that. Same thing for C, taking half. So it's a smaller amount. This word right here, depreciates, means to lose value. For D, F, and G, we know that these are growth functions. Again, the word growing is a dead giveaway that it's growth. And we know that it's a percent, so very likely it's going to be an exponential function. In D, the word here that kind of gives it away is interest. You earn interest on a bank account. In activity 4, now we're taking the idea of growth versus decay and percent and turning it into an actual function. So we can take all that information. So in the first column here for the growth, we're given the initial value. It's everything that we started with. In the second column, we're given what the word would look like or what the growth would look like in terms of words. Appreciate at 5%, double, increases by 30%, and so on. Our first goal then is to turn that number into a percent, from a percent to a decimal. So we have an appreciation of 5% as a decimal that's 0.05. An increase of 30% is 0.3 as a decimal. An increase of 10% is 0.1 as a decimal. The trickier ones are the double and the triple. So doubling is essentially a 100% increase. You take your original amount and you add that original amount again. So it's a 100% increase. So our increase here is a 1. That's 100% as a decimal. Triples means a 200% increase, so our number there is 2. In the fourth column, we're finding the growth factor. Because we're growing, we're going to add that new percent to the 100% we already had. So effectively, we're just taking that decimal that we created in column 3 and adding 1 to it if we know it's a growth. So we have 1.05. This becomes 2. This becomes 1.3, and so on. Then we create our function using this setup. Initial value times growth factor to the x. So in our last column here, the fifth column, we have 1,000 times 1.05 to the x. Again, initial value times growth factor to the x. Same thing in the second one. Initial value times growth factor to the x gives us that equation. And nothing's different for any of the others. Where things change a little bit is decay. We're still going to follow a lot of the same process, but we're not adding that to 100%. We're taking it away. So if we depreciate at 5%, we're taking 5% away from 100%. So when we convert that to a decimal, we're going to subtract that from 1 to get 0.95. So now we have 800 times 0.95 to the x. Half means we're taking 50% of it away. So 0.5, 300 times 0.5 to the x. And that pattern continues. Now, in the subsequent activities, in Activity 5 and Activity 6, we're actually going to take that information, those growth factor, the exponential decay factor, and we're going to create functions from a situation and then use those to solve.